Hi, we're Group 48. Our project is the Novo drug design using sandwich transformer. Researchers discover new drugs through doing many tests of molecular compounds to find possible beneficial effects against a large number of diseases. At the drug discovery stage, thousands of compounds may be potential candidates for development as a medical treatment. After early testing, however, only a small number of compounds look promising and call for further study. Drug discovery is a very time-consuming and expensive process. The average time to design one drug is 10 years, and average cost is $2.6 billion. The novel drug design is the process of generating novel lead compounds with desirable pharmacological and physiochemical properties. The application of deep learning in the de novo drug design has the potential to reduce time and cost of the process, and a pre-trained transformer model could solve small dataset problem.
In order to fast-track this drug discovery process, deep learning has played a significant role in this field, and one of the offshoots is Smiles transformer model, which has been started to be used recently. It essentially is a transformer autoencoder which takes in the Smiles input and decodes with the decoder. From the latent space, we extract molecular fingerprints, pass to an MLP, and get the target predicted values. We aim to improvise this Smiles transformer using the concept of sandwich transformer, which essentially is the rearranging of transformer layers with specifically the feed forward layer. The dataset which we'll be using to train this baseline smile transformer is Campbell 24, which essentially has 1.8 million molecules. On the left, you can see the corresponding smile structure of the molecules. After training our model, we will use molecule net datasets, HIV, BACE, and blood-brain barrier to predict if the given molecule is having that particular molecular property or not. Accordingly, we also generate vocab and corpus files from the dataset with 45 symbols. And the sandwich transformer will be using coefficients 1, 2, 3 for both encoder and decoder and get our results.
Now we talk about the pipeline and the architecture. For the vanilla smile transformer, we have 4 layers for our traditional encoder and decoder. So now we're trying to try sandwich coefficient of 1, 2, and 3 for either our encoder or decoder. Also, according to the paper, we should still leave some of the interleaving structure, interleaving layers in our encoder and decoder. So that's why we're not trying sandwich coefficient of 4. And then we'll get DEM scores of all these 6 experiments, and then compare with the vanilla smile transformer DEM values. This is what our pipeline looks like. We'll first perform a molecular fingerprint extraction by doing a semi-unsupervised training with our transformer, and then use the encoder part of the transformer to perform fingerprint extraction. And then we'll use the extracted fingerprints to pass it through a simple MLP for classification. And then eventually we'll calculate the data efficiency matrix by doing some different random splits of trained data and test data with different size, and then average their scores. So this will be a closer look into our transformer. So we have a decoder, we have an encoder and then decoder, and then the encoder can be used for extraction of the fingerprints.
And so our results are displayed here. On the y-axis for the 3 plots is the AUC mean, and the x-axis is the fraction of the dataset used for training. As you can see, the sandwich decoder coefficient 1, 2, and 3 models performed better than our baseline model for the HIV and base dataset, but all of our sandwich models performed worse for the blood-brain barrier dataset. And so to understand why some models perform better than others, we visualized the model's latent space for HIV molecules, and we reduced the dimensions of the molecular fingerprints to 2 with TSNE, a common dimension reduction technique. And as you can see, decoder 1 on the far right displays a feature space that is much simpler with less loops and branches, and there appears to be better separation between the positive and negative classes for classification. And so in conclusion, sandwich decoder 1, 2, and 3 improved well in DEM scores over baseline scores for datasets HIV and base. And in the drug discovery process, our study displays better potential and prediction of molecular properties for unlabeled datasets. Thank you.